So next we're going to talk about the precise definition of a limit. This is also called the epsilon-delta definition of a limit. So let f of x be defined for all x over an open interval containing a, and let L be a real number. Then for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus a, which is less than delta, this is delta, then f of x minus L is less than epsilon. Okay, this is the epsilon-delta definition of a limit. Now, let's figure this out a little bit more intuitively, and then we can go on to more formal definition. So, if I have a function that's continuous over an interval, right, here's f of x, and I have some value c that corresponds with a value epsilon, right? Then, that corresponds with a value, this is my limit. Then there exists some tiny delta as I get closer and closer. So I've got c plus delta, c minus delta, L plus epsilon, L minus epsilon, and these all correspond. Well, it should have been over here. But these will all correspond to values. So this isn't super mathematically rigorous, but as x approaches c, f of x approaches the limit. This is kind of a more gut one. So let's take a look at how to prove limits exist using an epsilon-delta form. So here's the formal epsilon-delta. So let f of x be defined for all x equals c on an open interval containing a, and let L be a real number. Then the limit as x goes to a of f of x equals L if for all epsilon greater than 0, every epsilon has its own delta greater than 0, such that if 0 is less than x minus c, which is less than alpha, less than delta, then f of x minus L is less than epsilon. So how might I go about using this to prove the limit? So here I have a problem-solving strategy. So you have to let epsilon be greater than 0, choose a delta value, prove this statement, and based on that show these both are true. And therefore f of x as x approaches a has this limit that we've defined. So let's do an example. I have f of x equals 2x when x doesn't equal 5, and x when x equals 5. So this has a removable discontinuity, okay? Its graph looks something like this. Okay. So when x equals 5, we have that our y value is going to be 10. So we know intuitively our limit is 10, right? We know that intuitively that that's what our limit's going to be. But now we need to prove it. So I've got to figure out some value for delta. So if I took x minus 5 is less than delta. We need this to look like f of x minus our limit is less than epsilon, okay? So let's multiply this by 2, right? So we multiply this by 2 on both sides. I get 2x, which is my f of x, minus 10, which is our limit, is less than 2 delta, okay? So let's let 2 delta equal epsilon. So delta equals epsilon over 2. So now we have let epsilon be greater than 0 and delta equal epsilon over 2. Thus, 2x minus 5 equals 2 times x minus 5 over 2, which is less than 2 delta, which equals 2 times epsilon over 2, which equals epsilon. So I showed an epsilon that was less than, that delta had a unique epsilon. So therefore, my limit as x goes to 5 of f of x equals 10. We should probably do another example. So the limit as the limit of 3x minus 2 as x approaches 2 is 4. So I have x minus my a, right, is less than delta, and I need to get this to look like f of x minus L. So I'm going to multiply both sides by 3. That gives me 3x minus 6 is less than 3 delta. But this doesn't look like this just yet. I need to rewrite it. So I have 3x minus 2 minus 4 is less than 3 delta. Okay, so I need to pick an epsilon. I'm going to let delta equal epsilon over 3 in this case. So that means I have 3x minus 2 minus 4 equals 3x minus 6, which equals, sorry, I need to remember my absolute values, 3 times x minus 3, which is less than epsilon. That gives me 3 times epsilon over 3, which is just epsilon. So we've proven our limit. Oh, right, let epsilon be greater than 0 and delta equal epsilon over 3. Then all of this. So limits from the right and limits from the left. So we can also use this epsilon delta form for when we're just using limits from the left or limits from the right. So let's take a look at f of x equals the square root of x minus 4. And this, we're going to find the limit as x approaches from the right, which we can already see will be 0. So we're in this case going to let delta equal epsilon squared. That means that x minus 4 minus 0 is less than epsilon, and we can assume 0 is less than x minus 4, which is less than delta. Thus, 0 is less than x minus 4 epsilon squared. So I can take the square root of all this. So I get 0 is less than the square root of x minus 4, which is less than a single epsilon because we're taking a square root. Thus, the absolute value of x minus 4 minus 0 is less than epsilon, and hence our limit as x approaches 4 from the right of the square root of x minus 4 equals 0. Now I want us to prove a limit does not exist using our epsilon delta equation. Sorry, using an epsilon delta proof. So this graph, I want you to know, it has a huge jump discontinuity once it gets to switches from negative numbers to positive numbers. So this graph is going to look something like these, right? It's just going to be 1 over x over at 0. Okay, so let's suppose L is a candidate for an limit. So is L. And let epsilon equal a half and delta is greater than 0. Either way, our limit is greater than or equal to 0 or less than or equal to 0. If my limit is greater than 0, we're going to let x equal negative delta over 2. Thus, x minus 0 equals negative delta over 2 minus 0, which equals delta over 2, which is less than 2. And if I was to substitute in delta over 2 into our function, I get negative 1 minus L, which is the same as L plus 1, which is greater than 1, which is greater than a half, which equals epsilon. And coming at this from the other direction, delta over 2 over delta over 2 equals 1 minus L. This value of L plus 1 is greater than 1, which is greater than 1/2, which equals epsilon. So that means that f of x minus L is never less than epsilon, and thus the limit doesn't exist at this point or equal L. So does not exist.